PhD dissertation defense was on realistic modeling of catalytic surfaces. Did a general lack of computational approaches in material science inspire you to pursue this topic?
Yeah, so honestly, it wasn't so much a lack in the approaches. There's been some very popular approaches to study, solid phase materials for now 30 years. The main method is something called density functional theory. And if you follow and you take quantum mechanics courses later, on in your professional development, you'll learn a bit more about, you may learn a bit more about what this method does. But in general, it allows you to calculate the thermodynamics, of surfaces and to build phase diagrams, which basically show as a function of pressure, temperature, and potentially other variables, what is the phase that is most likely to form under those conditions. And so I think in that respect, people were studying chemical reactions on surfaces, and the natural inclination is to take a material, which I'm working with solid phase, solid state materials. So they're crystallographic. They are, at least if you were to look at them, you'd see a repeating unit in all directions. And so what you can do is you can generate a cell that contains a small number of atoms, but that repeats itself infinitely through, the clever creation of what's called a boundary condition. And so then you can just simulate a few atoms. And so what people usually do is they create these cells, and then they get rid of some of the atoms. And so that exposes a surface, basically. It's a way of simulating a surface. The problem is, though, is that when you put a material under different conditions, that surface can actually change its structure and its composition depending on the environment. So if you take, for example, iron, iron is, it's commonly used in lots of, alloy materials. However, if you allow iron to just sit out in ambient conditions, it'll ultimately oxidize and form rust. What you see is rust on, like, anything metal that you may have. And so that's the surface changing its composition and changing its structure. And so this can happen under even milder conditions than, ambient. And so it's really important to have a good picture as to what is the stable state of the surface before you want to look at some, more complicated process like a chemical reaction. And so that was the heart of my research in my PhD. And it all started because we wanted to look at a catalyst, and it was a catalyst, an electro catalyst. And so that's a little bit different. Basically, instead of being in ambient condition like iron and air upon rusting, it's actually you put a material to the water, and then you hook that material up to a potential, and you can drive a current through it. And that current, essentially, you can drive electrons to the top of the surface, and those electrons can then jump onto a molecule and cause either the molecule to split and to form new bonds and to basically create products that are different than the things that you started with that are more useful, potentially. And so the idea was to study that reaction and to understand the mechanism. Then I quickly found that if you apply a potential, then actually the stable state of the surface changes. And so then the mechanism changes. And so for me, that was an important step, that was an important moment for me in understanding these surfaces, not just are the molecules, the reactants undergoing a reaction, but also the surface is changing. And how do those two play together? And I just didn't think that the current state of the field was considering that to the depth that it needed to be considered. And so that's the goal of my current research, is to try to, build tools that are really accessible and usable by everyone in the field. Yeah. So that they can start making even more informed decisions about, what's going on at a surface.
Yeah. And why are you excited about the prospect of utilizing more and more machine learning to discover the relative importance of structure and charge descriptors for materials design?
Yeah, so I think machine learning, it can be a great tool. I think that it's important to, as a chemist or a physicist, someone in the physical sciences, we always want to find a model that has a really strong intuition, something that a function that we can look at and say, I understand what that function means. It plays into my knowledge of chemistry and physics. It makes sense, right? So we want that, but and in some cases, machine learning can be very black box. So there are things like, neural networks where you are basically taking a linear regression, and then you're calculating all the correlations between all of those variables. And then you calculate all the correlations between all the correlated variables. And then you keep doing that. And so you've built this very complex network of correlated interactions, and that, you know, it may find precisely what the model is, but it may be hard to, you know, decipher, you know, is there a simpler, more, you know, chemically or physically intuitive model that could help me understand the real bottom line basic elements of the chemistry or physics in that scenario. And so I love applying it in the sense that I allow it to aid me in discovering trends. And so I do a number of simulations, and then what I can do is, if that simulation creates quite a bit of data, then I can pass all of the data into the, you know, the machine learning algorithm, whether that's a neural network or, you know, a simple linear model or even a random forest. I can pass the data into that, and it can find trends for me, and then I can use tools to probe, you know, what are the most important features that were found by these different you know, algorithms. And then I go back and I plot the correlations between the property that I'm interested in versus things that can describe the system, descriptors of the system. And then by plotting those correlations, I can then try to extract a chemically intuitive understanding of what the model found. And so it's almost a way of, you know, it's like machine assisted model building. I'm not going to rely solely on a machine learning model, but I'm going to use it to help drive me towards a physical model. And so that's the way I like to use machine learning. But there are very exciting applications of machine learning these days that basically the gold standard of a, you know, any chemical simulation is a quantum mechanical simulation that includes all of the quantum mechanical interactions between the electrons. And so in order to do that, you know, you need supercomputers and you need lots of processors. But people are finding ways to take machine learning models and to learn how the quantum mechanics predicts the energies of the system. And so in that sense, as long as you benchmark the machine learning model well enough, there may be scenarios where you can use a machine learning model to simulate a very large system at a very high level of accuracy, which is very exciting because, especially for engineers, at the end of the day, the most important thing is to make a difference, is to, you know, develop some new technology that revolutionizes a field. And so in that sense, you know, if departing from, you know, a purist quantum mechanical, you know, simulation gets us there, then so be it. And so there's a whole balance right now between how to apply machine learning and you know, it's you know, how it should be applied in different contexts, but in general it's very exciting and there's many ways to apply it.
Yeah. So the Monte Carlo simulation is named after Monte Carlo, where there's lots of casinos, and in a casino probability plays a big role with all those games. So why did you choose to use the Monte Carlo simulation?
Sure. So Monte Carlo is one way of getting at the macroscopic property of a crystal. And so if you can imagine, there are two ways that you could observe a system. You could either observe a system over time, which makes the most sense from our standpoint, right? You start an experiment, you measure some property as a function of time, and then you can, if it's at equilibrium, you can just average that property, and that's the time average of the system. There's another way to view a system, but it's more from a microscopic standpoint, that, you know, you don't think of the time as being your coordinate, you know, of your simulation, but rather the realization of the system. Another way to think about that is, let's say you have just a hydrogen or an oxygen molecule, right? You have two oxygens next to each other. At one point in time, the system might be here. At another point in time, the bond may have stretched or it may have contracted. And so instead of simulating as a function of time how that bond vibrates, which can be defined, you could just simulate different, you know, you could just create different stretches of the bond and then determine at that point in time, how probable is it to retain that particular configuration of the system. And so that's the more Monte Carlo approach, where you sample an ensemble of structures as opposed to allowing the system to evolve over time. It's two ways of getting at a an average property of the system. And in principle, if, and you'll learn about this concept potentially later on in your studies, there's a property called an ergodicity. Ergodicity means that the time average of a system is equal to its ensemble average. And so in certain cases, you should have the property that if you were to simulate something as a, over time and simulate something over a different realizations of the configuration of the system, that they should be the same. And so that's one of the guiding principles of Monte Carlo. And so I decided to use that because there are well-designed codes and frameworks for implementing the type of Monte Carlo that I was interested in, which is grand canonical Monte Carlo. And in that, basically here, I'll try to give you an example as to, how it relates to, the probability of a casino. So imagine you have a surface, and then you take that surface and you say, okay, well, there are a few possible moves that you could make. You could either move one of the atoms in the system, so you could just take it and you could just kind of push it, in any direction, any way you wanted to. But that's just a regular Monte Carlo move. But then there are what are called grand canonical Monte Carlo moves, where you could say, well, you know what I'm going to do? I'm actually going to move an atom into the system, or I'm going to pick an atom and I'm going to move out. And that's your selection of moves. And so then what you do is with a random number, you just decide, am I going to move something? Am I going to remove something? Or am I going to add a particle? Then once you decide that, then if it's adding a particle, you have to decide where you're going to put it. And so you can do that randomly too. If you're going to remove a particle, then you just select one and you remove that. And if you're going to displace a particle, you have to pick one, and then you have to choose how far and in which direction that you'll move it. And so what you do is then you calculate, before the system, you apply the change on the system, you calculate the energy of the system. And then at the end of the move, you calculate the energy again. So there's an old and a new energy. And then based upon whether the energy decreases, and if you recall from thermodynamics, in general, you want the system, a stable system will have a minimum in the free energy under, constant temperature and pressure conditions. And so if the energy goes down, then you accept that move. If the energy goes up, then you roll a die again. And you say, if my random number is, if I get a particular random number that corresponds to the increase in the energy, then I actually accept a jump up in energy. And so that actually allows the system to go over some hills. And so ultimately, it's a game. With a few moves, you roll the die and you see what you're going to try. And then over time, it samples all these different possibilities, and it finds itself at the bottom of a hill, in a valley. And no matter what move you choose at that point, it just stays in that valley. And so that's the most stable state of the system. And so that's why we chose that game to play.
Yeah.